Hey everyone, how are you? Today we're going to take a look at something super cool, which is logic gates that we usually study, right? The simple basic vanilla logic gates are not, and, or, XOR, NOR, right? So we have these logic gates that are we use them for different things. They have their own truth table, right? If you want to look at the truth table, this is what we're talking about. But this week, I released a course that involves digital electronics, right? Creating an actual computer, looking at hardware level, looking at this implementation, bits, circuits, and all those things. And it's super cool. And in this course, I told everyone that all those logic gates, they are usually, the implementation in hardware, they actually use NAND gates instead of using XOR or and NOT. And the reason for that, we actually went into details and I proved that it is actually cheaper and more efficient and easier to build circuits. Instead of using AND or NOT, you just use NAND gates. They use less transistors inside than those other things, right? It seems a little bit counterintuitive at first, but yes, a NAND gate has less transistors than an AND gate, right? I remember when I was a kid, it didn't kind of make sense, but yeah, we just saw that a NAND gate is easier and cheaper to build because it has less transistors than the equivalent ones. All right? My point right here, and the reason that I am bringing this to YouTube is because I want to have a lecture on, I just want to prove to you that NAND gate can be equivalent. We can implement all those 4 basic logic gates using NAND gates. So we're going to take a look at some Boolean algebra. We're going to kind of exercise our math muscles a little bit, and we're going to look at how we can prove that the NOT can be implemented using NANDs, the AND can be implemented using NANDs, the OR can be implemented using NANDs, and the XOR as well can be implemented using NANDs. We're going to kind of look at some logic derivation for those things, and also circuit format, right? So how can you actually have a circuit that implements all those things only using NAND gates? Quick parenthesis, when it comes to math notation, there are these kind of 2 schools of thought about math notation in terms of logic gates and logic and Boolean operations. When I was a kid and I was studying things like philosophy or even circuits in computer science, this notation right here was quite common, right? So if you open books, you would see that the negation was this NOT symbol A, right? So if I have A and I have a NOT gate, this was a negated A, this is the result. To get an AND operator, you have A and B, this is the conjunction operator, very common as well. The disjunction, this is the OR operator, so A or B, and the exclusive OR was this thing right here, very weird, but yeah, so A exclusive OR B, this is usually what you find in books. And you will see as well, the NAND operator in this set of notation is this thing right here, is this conjunction with this little negation bar at the bottom. Okay? But in Boolean algebra, there is also a school of thought that uses different notation, which is this one right here. So you will see that to negate an input, you will find a bar at the top, and this is very common in circuits, right? You have the inverted, the negation of a pin value, or have the negation of a bit. So this thing right here, very common, right? This is the negation. Keep this in mind. We're going to use this a lot in our lecture. AND is kind of the equivalent of a multiplication, if you want to think like that, right? So we're going to have A and B. We'll use this multiplication. To implement the OR, you're going to find a plus operation. You see, Boolean algebra is going to try to create this relationship between Boolean values and try to bring that idea of working with Boolean values almost as if we were working with addition and multiplication. So it tries to join these both worlds together, where multiplication and addition, they kind of make sense in terms of AND and OR. And this symbol right here is not that common, but you will see this is the exclusive OR for this set of notation right here. And super common, this one right here, this up arrow, is the NAND operator. All right, so we're going to take a look at these things. Keep this notation in mind. We're going to use them a lot now in our derivations and in our proofs. Okay, so let's just start. I want to tell you that it is possible for us to use only NAND gates to implement an inverter, right? This NOT gate. how do we go about doing that? So I'm not using NAND gates. We want to get not A, right? So this is what we want. We want A negated. I'm going to propose something to you. This is actually not that difficult to come up with a solution. So if you want to pause the video right now and try to get some pen and paper and do it yourself, you're going to see that it's quite easy for us to get an inverter only using NAND gates. So stop the video if you want to implement that yourself. It's a lot more interesting if you come up with the solution before I show, right? So go ahead, pause the video, and I'll give you a couple of minutes, and we're going to come back very soon. So coming back, right? I want to get this thing right here. How do I go about using NAND gates? So let's just think about what a NAND gate really is. If we perform a NAND, right? So let's just take our input, because we just have one input for the inverter, right? So if I get my input and if I NAND with itself, I end up with this thing right here. Because think about what a NAND really is. NAND is an AND negated. Right? So do you see it is the input A and input A negated. This is what a NAND is by definition. But the good news is that if I take an input A and I AND with itself, A and A, this is always going to be A, right? This is equivalent to just A. So this thing right here is equivalent to just A negated. And that is pretty much it. If I want to negate A, I can just NAND that input with itself. And if you stop to think about it, it's quite reasonable, right, that we came up with this conclusion. And if we look at the circuit implementation of this, I think it's even easier to understand, right? If I get my input A and I just NAND with itself, this split right here doesn't do anything. I end up with A just negated here at the right-hand side. So for me to negate something using NAND gates, all I have to do is just NAND that input with itself. Check. So the first proof, right, I'm going to call this proof, but it's just us breaking down step by step, trying to come up with this intuition behind these symbols and behind this notation. And I think the circuit is quite clear what we're doing, right? Just inverting that input. There we go. I am going to start now on the right-hand side here. I'm going to start listing everything that we have been proving so far, right? So if I just prove that not A is A NAND A, I'm going to leave right here this not using NANDs. We just came up with this final solution because, look, chances are we're going to use this thing that we already found in future proofs as well, right? As we are proving AND and OR and XOR, we might have to use this thing right here. If we find a not, maybe we can just replace by A NAND A. Cool, so right here on the right-hand side, I'm going to keep listing everything that we have been proving so far. Every result, I'm going to just start piling up here on the bottom. All right, beautiful. So let's move on. Let's just go to the next one. How about ANDs? I want to prove to you that I can have an AND truth table just by using NAND gates. So this is what we want. We want to reach A and B. I am going to start by thinking about a NAND gate, by this NAND operator. What is, by definition, a NAND operator? So look, by definition, if you think about A NAND B, if you have these two inputs and you NAND them, this is equal to the first input and the second negated, right? It is a NAND gate. I AND and I negate. So look at this thing that you have right here, which is a NAND gate. And if we have A and B negated, and what we really want to achieve is this thing is A and B, do you agree that we can basically negate this thing and we're going to get to what we want? So we're just going to negate it, right? To get to this pure non-negated version. So if I go and I negate this one, I get A and B is equal to this thing right here, A NAND B negated. So A NAND B negated. That's what we got from this negation here on the top. Right, so what we have right now is we have A NAND B, so we are getting closer to our solution, but we still have this not here at the top, right, that we need to replace. We need to substitute by a NAND. How do we do that? Well, we know how to replace a NOT with NANDs. We found this before, right? So I just NAND with itself. So if I get this A NAND B and I NAND with itself, I'm going to get the solution that I want, right? So just replacing that NOT, this big bar here, from what we learned from this first proof of the NOT, we're going to replace this whole thing. Therefore, A and B becomes A NAND B, NAND A NAND B, right? Because I just NAND this thing with itself. That is how I negate it. And look, I'm pretty happy because all this equation is only consisted of NAND gates. So this is pretty much our result, right? So if you want to go ahead and implement the circuit version, pause the video and implement, right, the whole circuit version using NAND logic gates. But my implementation is pretty simple. If I want to implement this in circuit format, I'm going to have my inputs A and B. Do you agree that I have to NAND A and B, and then I NAND A and B together? So I get A NAND B, A NAND B, so I NAND A NAND B, and then I get the result of this A NAND B and NAND B, and I NAND with itself. So this big NAND is this inverter right here that I have, right? And the result is A and B, the truth table of the AND gate. And I told my students in the course, I said, look, when I was a kid, it didn't make sense, right? Because I thought that a NAND gate, right? In my mind, when I was a kid, I thought that the NAND gate was an AND inverted. But in reality, in most circuits, is actually the other way around. An AND gate is actually a NAND inverted. So this is actually what we see in the wild, right, out there. This is usually what you see implemented via hardware. Cool. So this is the end. Hopefully now we got an idea of how we're going to evolve from here, right? This is what we're going to do from now on. We're going to look at these properties. We're going to start expanding them. We're going to start replacing. We're going to start negating using what we already know for the proofs. And now we just found out that A and B is this thing right here. So I'm going to just pile up here on the top right. Let's just say that the AND using NANDs is this thing right here, because chances are we're going to have to use this in future proofs, right? If we're going to look at OR and XOR, there might be cases where we're going to look at a NOT and an AND, and we're going to have to just replace them by these equivalent NAND versions that we already have. Good stuff? Cool, so let's just go ahead and look at the OR gate. So if I have an OR gate and I want to implement this truth table of the OR gate only using NAND gates, and you will hear people sometimes talk about NAND gates as Sheffer stroke. So it's basically the same thing. You will hear a NAND gate also being called a Sheffer stroke in the math world. But at the end of the day, it's the same thing. Sheffer stroke or NAND gates, this is what we are after. Right, so what we want is this thing right here. And everyone, do you see how I have an OR? And an OR and a NAND gate, they don't have really much in common, right? Do you agree? If I just look at this thing, how can I get closer to what a NAND gate needs? Because a NAND gate, I think an AND is a lot better than an OR, right? In Boolean algebra, how can we replace an OR with ANDs? And if you are a programmer, you probably know the answer already. The answer is usually something called De Morgan's law. And just to give a quick review, right? Using De Morgan's law, you can replace, for example, A or B by the equivalent using AND and NOTs. So if you look at the property, De Morgan tells us that to replace A or B, I can rewrite this by using not A and not B. Okay, so this is a property, this is a law that if you are a programmer, you probably use this a lot, right? Whenever you are writing your if statements, your while statements, whenever you have these checks and tests, these conditionals, sometimes to replace an or replace an and, we use De Morgan's law, right? This is quite common for us in our day-to-day coding rituals, right? So De Morgan's law states that A or B is equals to not A and not B. So I'm going to come back here where I have this OR, and I'm going to expand and replace using De Morgan's, right? So if I use De Morgan, I'm going to replace this OR by the negation of not A and not B. Because do you agree that having this AND here gets us a lot closer, it's a lot better for us to kind of try to get to the NAND result that I want, right? Instead of having that OR there. So just using De Morgan's, I kind of already found an AND here. So let's look here, and what do we have? We have not A and not B negated, right, bar. Can we replace and substitute these nots? Yes, we can, because we already know how to replace nots using NAND. So let's just go ahead and do that. Replace this A with a not, this B with a not, and we can actually replace the whole thing because the whole thing is a NAND gate. So just substituting this not A and this not B, right? Not A is A NAND A from this thing right here that we just saw. So not A is A NAND A, and not B is B NAND B. So let's just replace this whole thing right here. And as you will see, in the moment that I replace A NAND A and B NAND B, this thing right here became a NAND gate itself, right? Because it is the first and the second negated. So I can NAND those two terms, the left and the right, together. This is my OR gate. Check, we are done. Do you see? Easy, right? In the moment that you understand De Morgan's law and you can substitute this OR by something a little bit better for us to actually get to our NAND gate, right? An AND is a lot better than an OR. So I just use De Morgan, I start replacing those nots, and I get to my solution, which is this one right here. Do you want to pause and do the circuit yourself? It's quite easy, right? You can pause the video and we're going to look at the implementation now. So if you want to just implement this thing, it is the input A, the input B. So let's just look at what we have. I have A NAND A, which is this first NAND right here with an A NANDed with itself. I have B NAND B, which is this one right here, just NANDed with itself. And then the result of the first and the result of the second, I NAND together with this big NAND that joins the left and the right. I join with this big NAND and I get the result, which is my OR logic operator that is implemented using NAND gates. Cool stuff, right? Beautiful. So there we go. So now that we have this thing right here, let me just add that on the top right. Now our OR using NANDs is this thing right here, is just AND NAND A NANDed with B NAND B. So this is how I implement OR only using NANDs. And we are moving to the last one that I want to cover, which is the exclusive OR. I'm not going to lie to you, the exclusive OR is a little bit more annoying. It has some extra steps, but it's nothing too complicated. If you understand De Morgan's, if you understand NOT, NANDs, and all those things, it should be pretty easy for us to find a solution. So let's go ahead and do the last one. So how can we implement the truth table of the exclusive OR using NAND gates? This is our goal. Right, so let's just pause for a moment and think about what really is an exclusive OR, because this is not that common. Sometimes people are not very familiar with it. So if we look at the truth table of the exclusive OR, this is what we get. So input A, input B, and the exclusive OR result. The exclusive OR truth table is very, very similar to an OR operator, but the only difference is that it does not allow for both inputs to be true at the same time. So if A is 1 and B is 1, the result is false. So look at what we have. 0 XOR 0 is 0. 1 XOR 0 is 1. 0 XOR 1 is 1. But if both A and B are 1, the XOR is false. Do you see? It excludes the possibility of both A and B are together 1. So this is the exclusive OR. It's almost like an OR excluding the possibility of both inputs being true at the same time. Right, so I want us to pause and look at what this truth table is telling us. Right, look at really the output when it's true and when it's false. If you look at the truth table, you can think of the XOR. You can kind of rewrite the XOR using some identities. So I'm going to show to you what I'm calling the XOR equivalent identities, right? And look, I know that this sounds a lot of kind of notation and math, but if you think about what this means, it kind of makes sense. So look at what it says. A exclusive OR B is equal to A and not B, or not A and B. Pause for a moment and think beyond the formula, right? Don't look at just the dry formula. Try to hear what I'm saying in English. The result of the exclusive OR A and B is the first input and not the second, or not the first and the second. The exclusive OR is only true when the first input is true and the second input is false, or when the first is false and the second one is true. That is exactly what we have here in our truth table. When A is 1 and B is 0, then XOR is 1. When A is 0 and B is 1, XOR is 1. Any other option is false. So do you see, this is just me kind of writing. This is an equivalent property, an equivalent identity that I can use to replace that ugly XOR symbol, but using things that I already know. I already know AND, I already know NOT, so this can come in handy. But you can also rewrite an XOR a little bit different. There's another identity which is equivalent as well, which is this one right here. So look at what it says. A XOR B is also equals to A or B and not A and B. I'm trying to explain things in English already, right? Just hear what I'm saying. Exclusive OR is true when A is true or B is true, and not A and B. So I'm kind of getting that the XOR is true when A is true or B is true, but I'm excluding, right? I'm kind of combining this AND. And also I have to guarantee that A and B are not true. So A and B cannot be both true. I am excluding that. So do you see how, if you look at the equivalent identities, it's not hard to really grok them, right? To really understand what they mean. If you just look at a math book and you just look at these identities, it's very weird, right? It kind of doesn't resonate much. But if you stop and you look at what it's telling you, these identities make sense. You just look at the truth table and it's kind of like, okay, the first one is true, the second one is false. So the first one is false, the second one is true, then that is an XOR, right? That is exactly what an XOR is. Or the other way around, is the first or the second, but also I have to guarantee that AND, it cannot be first and second. Right? So I just wanted to kind of understand why these identities are here. And look, for us to start replacing and expanding this XOR, we can pick either one of these properties, right? I'm going to pick the first one because I think this is the most common proof that I see in books out there. Let me just pick the first one. Let's just go with the first one. Let's just rewrite that XOR in terms of this first one, A and not B, or not A and B. Cool. So let's just get this one, and by definition, as we just saw, A exclusive OR B is A and not B, or not A and B. Because having ANDs and NOT is a lot better than having this ugly symbol right here, right? And we already know and not, we already know how to replace all these things we saw before. So all we have to do is just replace these things and find the NAND equivalent. Right, so we're going to start by doing something a little bit weird at first, but bear with me for a second, it's going to make sense very soon. So what I'm going to do is, I am going to add to this term right here, I'm going to add a couple of zeros on the right-hand side. So I'm going to expand with zeros this thing that says A and not B, or not A and B, plus 0 plus 0. And this plus 0 plus 0 is not going to change anything, right? But it's going to be important for us because I want to replace the 0 by some useful properties here. So let's just look at some property. Do you agree that if I take one input negated and the same input, this is always 0? I think we don't even need to prove this one, right? If I have not A and A, there is no way that this is going to be 1. 0 and 1 is 0. 1 and 0 is 0. So it's always going to be different. And for an AND to be true, they have to be both the same. So this it will never be true. So not A and A is always 0. And equally, not B and B is always 0. Right, so I'm going to replace this 0 by the A version of this thing, and I'm going to replace the second 0 with this not B and B. So I'm going to go replace this to 0, and I'm going to get this thing right here. A and not B, or not A and B plus not A and A, plus not B and B. So these two are the old zeros that I had, right? They are not changing anything. I'm just adding them here because it's going to be easier for us to start grouping a couple of things. Very well. So now that I have this whole long equation right here, one nice thing about Boolean algebra is the fact that, do you see how we are using these symbols? Almost like a multiplication for and an addition for or. So Boolean algebra tries to link these two things, right? It kind of brings the whole mathematical notation that we are already used to with numbers and tries to apply for this binary logic inputs, right? True or false. So what I can do right here, which is quite interesting, is the fact that I can look at common terms and then I can factor them out as I would do with a normal number. So for example, A and not B, and I already have also another A here. So A is a common term for this term and is a common term for this term right here. And I also have B as a common term here and a common term from this last one. So I can basically just pull A and B out and just multiply by whatever is left. Let's do that. So just factoring the common terms, I get A, I factor that A out, and then I multiply by what was A multiplying. So A was multiplying not A, so not A, plus A was multiplying right here not B, so not B. So between parentheses, I just multiply by that or combination, A as a common factor outside, and I'm going to do the same thing plus now the B as a common factor. What was B a common factor of? So B was a common factor of not A, and B was a common factor of not B. So not A plus not B. Right? So just factoring out A and B as we would do with normal vanilla numbers, right? But we are actually using logical Boolean inputs here in this case, which is super cool from Boolean algebra. This is what Boolean algebra is great for, right? These proper algebra manipulations that I have with Boolean values. Cool, so now that I have all these things right here, what can we do? Well, if you are already ahead of me, you probably noticed that I have an OR here, right? An OR between these kind of negated values. I have also here an OR between these negated values. Do you agree that it is a lot better if I try to replace this with an AND to get to our NAND output, right? So I'm going to apply De Morgan's law for this one and this one, right? Because De Morgan's law tells us that I can replace this not A or not B by the negation of A and B. This equivalence is true, so I'm just going to replace this OR between these two negated terms by something that is a lot better for me, right? Which is this AND negated. Look at that, an AND negated. I love it. So this thing is going to replace here and it's going to replace here. They are going to become, right, using the Morgans, this is going to become A multiplying the negation of A and B, or B multiplying the negation of A and B. Beautiful. So this is already looking good. But there is an extra step because this is not great if we want to just replace with NAND gates yet. I'm going to use a trick, which again might seem quite crazy at first, but it's going to help us replace all those things and start canceling things out. So look at what I'm going to use. Do you agree that there is something called a double negation law? And I'm pretty sure that you heard this before, right? if you have an input and you negate twice, you end up with the original value of A, which is quite easy to understand, right? If I have an input A and I invert, I get it flipped. And then if I flip again, I get the original value, right? So I negate and I negate, I get the original old value that I had unchanged. So that is exactly what I'm telling you right here. If you go and you negate twice, you basically are getting the same value as you had before. So I'm going to use this double negation right here, and I'm going to double negate this whole thing right here. Yes, I know it sounds crazy, but I'm going to double negate this big chunk of the right-hand side right here. So that double negation is going to end up like this. What I had before, double negation, right? And it sounds super crazy, but this is going to make sense because now I can start replacing and finding the NAND gates inside a lot easier. So let's just look at what we have. I have A multiplying A and B plus B and A and B negated, everything negated with a plus. Everyone, how can I replace this plus right here? You know the answer to that already. De Morgan's law, right? So I can use De Morgan's law to replace this big chunk of negation that I have inside by these two terms ended with itself. So just applying De Morgan's law in this big term, A or B negated, which is what I have right here, these two big terms, right? You can think about the left term as A and the right term as B. So these two things, or with itself negated, is going to become the first negated and the second negated. So just using De Morgan's law in this inner term of the negation, I end up with this left term negated, and this and is a lot better than that plus the second term negated here on the right. Right, just replacing this inner negation with an and these two terms now. Because if you look closely at what we have right here, everything here is already a NAND gate. Do you see? Look at this one right here. A and B negated. This is a NAND gate. A and B negated. This is an AND gate. You see how I have also around this negation here on the left and this negation here on the right? So everything here is already NAND gates, just one NAND gate inside itself. So let's just start replacing these NAND gates. This one right here, you can probably see, right? A and B negated. This is an AND gate. This is an AND gate. So let's just replace this first one, this inner parenthesis here. So just replacing the first NAND, I have A multiplying A NAND B, and this one is B multiplying A NAND B. Right, so what else? Well, we can replace this big one right here. Do you agree that we have one term and another term negated here with this big negation at the outer part? So let's just replace this big thing here by one big NAND. So replacing again the NAND, I have A and A NAND B negated, big NAND B and A NAND B negated. The only thing that is left is this negation here on the left and negation here on the right. But this one is easy as well, right? Because even though I am not showing a dot here, this A multiplying this A NAND B, there is an AND here between these things. So this is already an AND gate itself, right? So this is A and this term negated, so this is an AND gate, and this is B and A NAND B negated. So both of these things are NAND gates itself. So let's just go ahead and replace. Replacing these big NANDs here, I have A NAND B, right? So A NAND B, this whole thing NANDed with the right part, which is B NANDed with A NAND B, B NANDed with A NAND B. This is exactly what we wanted, right? This is an XOR gate implemented only using NAND gates. NAND gate, NAND gate, NAND gate, NAND gate, NAND gate. Check, we are done. So hopefully this all makes sense, right? I told you, it took us a lot more sweat and tears, right? Knowing De Morgan, expanding these zeros. I know that, look, expanding these zeros right here was not trivial, right? It took us a little bit of creativity to get there. And trust me, I didn't know this beforehand, right? I saw these proofs a long time ago and I kind of got some ideas out of them. So don't worry if you didn't come up with this yourself. I also saw this somewhere. But yeah, there we go. We kind of found our XOR only using NAND gates. Let me just copy this solution and right here on the right-hand side. So these are our results, right? The NOT using NAND is this, the N using NAND is this one right here, OR using NANDs is this, and then now the XOR using NANDs is this big chunk of NAND inputs right here, which is exactly what we see here on the left as well. As before, if you want to go ahead and implement the circuit of this thing right here, I think is a lot more interesting if you do that before we show it, right? It's a lot more interesting and satisfying if you go ahead and you kind of get the solution before I show it to you. All right, so pause the video, do that yourself, come up with the circuit, just implementing this thing using NAND gates, connecting those NAND gates together, and you know what? Let's just see what we get. All right, so the way that I like to do that is if we look at the implementation, I like to start looking at this inner parenthesis first. So look at this one, A NAND B, and I also have here in this inner parenthesis A NAND B. So I have inputs A, I have inputs B. This first NAND gate is responsible for performing that A NAND B inside here, this small A NAND B. So I get A and I get B and I NAND with each other. And then I get the result of this A NAND B and A NAND B, and I have to NAND with B and A. So the result of A NAND B, I have to NAND with A, and I have to NAND with B on this second NAND on the bottom, and I NAND with B. Correct? And then the result of this right-hand side and the result of this left-hand side, I have to NAND those two things with this big NAND in the middle. So the result of this NAND and the result of this second one with B, I have to go and NAND those two results, and then and only then I get my exclusive OR result. Beautiful, right? I think so. So look, this was our chance to go exercise. I wanted to show to you all this Boolean algebra, these logic operators, this math notation. As always, right? My goal is to enable you to go now that you know how these things work, you kind of lost the fear. This is an enabler, right? And it enables you to go and open a math book and not get intimidated by it. You kind of know how it works. You can kind of spend some time and, okay, now I understand. Now I can kind of set and understand, get something a little bit more in-depth, a little bit more rigorous. And it should be easy for us to go and kind of just look what's going on. But I thought it was important for us to pause, right? Enjoy this moment, savor these ideas of showing to you, right? Proving to you that a NAND gate is this, what we call a universal gate, that we can use NAND gates with everything else, right? I can use a NAND gate to invert, right? To have a NOT gate. I can use a NAND gate to have an AND gate. I can use NAND gate to implement OR. And as you just saw, I have NAND gate, only using 4 NAND gates, I can implement an XOR. And of course, I can use with a NOR gate, I can use with, you will see that we use a multiplexer, right? So multiplexers that we are using in our course, they are basically just a construction that uses simple logic gates. So if we use logic gates like ANDs and ORs and negation, a multiplexer can, of course, be implemented using NAND gates themselves. So all these things that we have been using, NAND gates, they are, right? It's very weird to say that, but in reality, most circuits that you have in our computers, most of them, they actually use NAND gates instead of an actual vanilla XOR, vanilla OR, vanilla AND, and etc. Right? So I thought it was important for us to stop, have some mate, and look at logic gates. And look, don't forget, right, if you actually like this content, if you want to dive into digital electronics, if you want to dive into creating circuits, understanding how a computer really works at the lowest possible level, right? I think this is the lowest possible level, looking at the atomic level, electrons, charge, moving electricity, current, resistors, impedance. So looking at these fundamental ideas of how a computer works and creating circuits and building stuff and using logic gates to create a register, to create flip-flops, to create latches, to create a bus, to create memory cells, to add stuff together, to subtract stuff, to create and compute stuff. If you want to understand from the ground up how computers really, right, what makes computer tick, I think you will really like our course on digital electronics. It's super fresh, we just released it. I'm quite happy that I'm able to bring this course to you at picuma.com. Just go ahead, visit us, and I think you're going to enjoy what we have there. All right, see you soon. Thank you.